Light is the very essence of vision, yet the ultimate blind spot of the cosmos. It shows us everything, but hides the true nature of reality just beyond its reach. The absolute mystery. Why does light define our existence? Human perception of reality is intrinsically linked to electromagnetic radiation, where light acts not only as an illuminator, but as the fundamental fabric of causality and the sole messenger from a remote past that defines the architecture of the present. Carl Sagan frequently used the analogy of the cosmic ocean, suggesting that humanity has spent a long time on the shores of this vast sea and is finally ready to set sail towards the stars, using light as our compass and our means of transporting information. Sagan compares life to butterflies that float for a day and believe that day to be forever, a metaphor illustrating the brevity of human existence compared to the timescale of light that travels for billions of years through a vacuum. The concept that we are star stuff underpins the idea that the light emitted by high-mass stars in the primordial past forged the atoms that today make up human biology, connecting the observer to the observed phenomenon in an atomic and chemical way. Brian Cox expands on this view by stating that light is the only connection we have to the universe beyond our solar system, acting as a messenger from the distant past that transforms the act of observing the sky into an archaeological exploration of time. The invisible barrier of the cosmos is defined by the speed of light, a constant that imposes an absolute limit on the speed at which any signal can travel, ensuring that the universe maintains a logical structure of cause and effect. Understanding light requires a shift in perspective where we stop feeling small due to the vastness of the universe and begin to feel great because our atoms and our consciousness are the way the cosmos knows itself. The geometry of the barrier, relativity, infinite mass, and the limit of causality. Light in a vacuum travels at a constant speed of exactly c equals 299,792,458 meters per second, a value that is not merely an arbitrary speed, but an intrinsic characteristic of the fabric of spacetime. The modern understanding of this absolute limit derives from the work of Albert Einstein, who revolutionized physics by demonstrating that space and time are not absolute, but relative to the observer and interconnected in a single four-dimensional entity. This interconnection implies that, as an object increases its speed towards the speed of light, time passes differently for that object compared to an observer at rest. The light barrier is maintained by the fundamental relationship between energy and mass. As a massive object is accelerated, the energy used to increase its speed translates not only into motion, but also into an increase in the object's inertial mass. This effect becomes significantly pronounced as the speed approaches c. For example, at 10% of the speed of light, the increase in mass is only 0.5%, but at 90%, the object's mass is more than double its rest mass. For a human being or any object with physical mass to reach the speed of light, an infinite amount of energy would be required, making the barrier physically insurmountable for ordinary matter. The relationship between velocity, mass, and time dilation becomes increasingly dramatic as an object approaches the speed of light, $c. At a state of rest, an object maintains its normal mass, and time flows at a standard rate of 1 second per second. However, once the object reaches 50% of the speed of light, the relativistic mass increases to 1.15x its original value, while time for the traveler begins to slow down, with only 0.86 seconds passing for every second recorded by a stationary observer. As the speed enters extreme ranges, these physical changes accelerate rapidly. At 90% of the speed of light, the mass more than doubles to 2.29x, and time dilation cuts the traveler's experience to just 0.43 seconds. This trend continues sharply. At 99% of $c, the mass jumps to 7.09x its rest mass while time slows to 0.14 seconds. Pushing even further to 99.9% of the speed of light causes the mass to swell to 22.37x its original state, with time slowing to a mere 0.04 seconds. The progression reaches a definitive physical boundary at 100% of the speed of light. At this theoretical limit, the relativistic mass becomes infinite, and time stops passing entirely for the traveler. This explains why objects with mass cannot reach the speed of light, as the energy required to move an infinitely heavy object would itself have to be infinite. Beyond the physical constraint of mass, light establishes the boundary of causality in the universe. Since no signal can travel faster than c, this limit defines the light cone of any event, determining which parts of the universe can influence one another. This constraint ensures that the effect always occurs after the cause. If light could be overcome, the chronological order of events could be reversed, allowing paradoxes where a result precedes its origin, which would destabilize the very logic of theoretical physics. Thus, light acts as a kind of chronology police, maintaining the integrity of cosmic history. The experience of light, however, is paradoxical when viewed from its own perspective. According to the principles of relativity, for a particle traveling at speed c, such as a photon, the distance traveled and the time elapsed are effectively zero. From the perspective of a photon emitted by the sun and absorbed by the retina of an observer on Earth, the birth and death of the particle occur at the same instant, although for the observer 500 seconds have passed. This disparity between the external perception and the internal reality of light is one of the deepest mysteries of physics, suggesting that light inhabits a plane of existence where time and space lose their conventional meaning. Measuring the speed of light was one of the greatest challenges in the history of science. It was the Danish astronomer Ole Romer who, in the 17th century, provided the first experimental evidence that light was not instantaneous. Observing Jupiter's moons, Romer noticed that eclipses occurred later than expected when Earth was farther from Jupiter, concluding that light took a finite time to traverse orbital space. This discovery paved the way for the unification of electromagnetism and relativity, transforming light from a simple optical phenomenon into a universal constant that anchors our entire understanding of the cosmos. The genesis of transparency. From the opaque soup to the first messenger. In the first moments after the Big Bang, the universe was an environment of thermal chaos and extreme density. During the first 380,000 years, the cosmos was characterized as an opaque soup, or a fog of incandescent plasma. In this primordial stage, the temperature exceeded 1 trillion degrees, and matter and energy were in a state of forced cohabitation. Free electrons, not yet captured by atomic nuclei due to high thermal energy, acted as constant obstacles for photons. Light could not travel anywhere without immediately colliding with a free electron, resulting in continuous scattering that made the universe impenetrable to sight. If there had been an observer in that era, they would have seen only a bright haze, as dazzling as the surface of a star in every direction. The transition from opacity to transparency was a physical event of singular magnitude, known as recombination. As the universe expanded, it also cooled. When the temperature dropped to about 3000 Kelvin, the energy of the electrons decreased enough for them to be captured by protons and helium nuclei, forming the first neutral atoms. With the formation of atoms, the electrons ceased their obstruction to the path of photons. For the first time in cosmic history, light could traverse the vacuum unimpeded, marking the birth of universal transparency. The history of the universe began with inflation and the Big Bang, a period characterized by incalculable temperatures where matter existed as a primordial plasma. During this initial stage, light was completely imprisoned and unable to move through space. As the cosmos expanded into the era of opacity, temperatures remained above 3000 K, keeping matter in a state of free electrons. In this phase, light experienced continuous scattering, acting like a thick mist that prevented it from traveling clearly. A pivotal shift occurred approximately 380,000 years after the start during the recombination era, when the temperature cooled to roughly 3000 K. This cooling allowed for the formation of neutral atoms, which triggered the release of photons, finally permitting light to travel across the universe. This was followed by the Dark Ages, where temperatures dropped between 3K and 2.7 K. During this time, the matter consisted of cold gas, and while light could travel, there were no new light sources yet in existence. In the current universe, spanning 13.8 billion years, the temperature has settled at 2.725 K. Matter is now organized into complex structures such as galaxies and stars. The behavior of light in this modern era is defined by transparency, though it is influenced by redshift as the universe continues to expand. This radiation released during recombination still fills the entire universe today, although it has been drastically altered by the expansion of spacetime. As the universe grew, the wavelength of these original photons was stretched, redshifted, losing energy and shifting from visible light to the microwave spectrum. What we detect today as the cosmic microwave background, CMB, is essentially the echo or photograph of the moment when the universe became transparent. The CMB acts as a fossil record, allowing scientists to analyze tiny temperature fluctuations that represent the seeds of future galaxies. The light from the CMB reveals crucial information about the composition of the universe. Through the analysis of these primordial radiations, it was possible to deduce that the cosmos is composed of only 4% ordinary matter, 23% dark matter, and an impressive 73% dark energy. Without light as a messenger, these invisible components of the universe would remain unknown. The transparency of the universe not only allowed stars to shine in the night sky, but also provided humanity with the ultimate tool to reconstruct the history of its origins from the very first second of time. However, even after recombination, the universe faced another period of partial darkness known as the epoch of reionization. Although the universe was transparent, no new light sources existed until the first stars and galaxies formed hundreds of millions of years later. These early sources emitted intense ultraviolet radiation that gradually ionized the surrounding neutral hydrogen, creating bubbles of total transparency through which light from distant galaxies could finally reach Earth. The study of this period is the final frontier of modern astronomy, and it is here that instruments like the James Webb Telescope play their fundamental role in deciphering the past. The James Webb Telescope and the archaeology of the first gleam. The James Webb Space Telescope, JWST, represents the pinnacle of human engineering dedicated to capturing ancient photons. Unlike its predecessors, the JWST was designed to predominantly observe the infrared spectrum. This technical choice is fundamental due to the phenomenon of cosmic redshift. As the universe expands, the light emitted by distant galaxies billions of years ago is stretched, moving from the visible spectrum to the infrared before reaching our detectors. Webb, therefore, functions as an infrared time machine that allows us to see beyond the barriers that limited the Hubble telescope. One of the most impactful discoveries of the JWST was the identification of the galaxy Jades, GS Z13-1, located at a redshift of 13.0, meaning we are observing it as it was just 330 million years after the Big Bang. Surprisingly, this galaxy exhibits a bright hydrogen emission signature known as Lyman alpha. According to current theoretical models, the universe at that time should have been saturated with opaque neutral hydrogen that should have blocked such radiation. The detection of this light suggests that the reionization of the universe, the process of clearing cosmic fog, occurred much earlier or in a much more fragmented way than previously predicted. The study of the early universe has been revolutionized by the detection of extremely distant objects, characterized by their high redshift, $Z values. The current distance record holder is Jades, GS Z14-0, which has a redshift of 14.32. Light from this object was emitted when the universe was only approximately 290 million years old, providing a glimpse into the very first stages of cosmic history. Similarly, Jades, GS Z13-1, observed at a redshift of 13.05, dating back to 330 million years after the Big Bang, has surprised astronomers with its unexpected Lyman alpha emission, a feature that challenges our understanding of how light interacted with gas in the early cosmos. As we move slightly further ahead in cosmic time, we find complex structures that emerged much earlier than previously expected. For instance, Source 1019 represents an early supermassive black hole that existed when the universe was approximately 570 million years old, even though its specific redshift remains unknown. Furthermore, the objects colloquially known as little red dots have been identified with redshifts ranging from 5.0 to 9.0. These objects, which date back to between 500 million and 1 billion years after the Big Bang, are characterized as notably compact and dense galaxies, offering vital clues about how the building blocks of our current universe began to assemble. In addition to detecting distant galaxies, the JWST revealed that the early universe was far more structured and chemical than expected. Heavy elements such as oxygen were found in galaxies formed only a few hundred million years after the beginning of the cosmos. Since heavy elements are only forged inside stars, this implies that the first generation of stars, the hypothetical population 3 stars, must have lived and died extremely rapidly, enriching the interstellar medium almost instantaneously on a cosmic scale. These stars were massive, hot, and composed purely of hydrogen and helium, acting as the universe's first chemical factories. Webb also brought to light what astronomers call the platypuses of astronomy, galaxies that defy conventional categorization. Some of these galaxies appear as tiny dots, resembling stars in our own neighborhood, but their spectrum reveals them to be immense galactic structures located billions of light-years away. The slow movement of gases in these galaxies, indicated by narrow emission lines, suggests a much calmer and more orderly galactic formation process than chaotic merger theories predicted. These observations indicate that light still holds secrets about how matter originally organized itself to form the cosmic tapestry we see today. Through infrared spectroscopy, JWST can decompose the light from distant stars and extrasolar planets to identify molecules essential for life. Light serves not only to show the position of objects, but to reveal their chemical recipe. Each photon captured by Webb's gold detectors carries with it the story of its origin, the gas clouds it passed through, and the expansion of the universe that stretched it. By translating these signals, modern science is finally beginning to understand how the light of the first glow shaped the conditions necessary for life to eventually arise on a small rocky planet called Earth. Time dilation, paradoxes, and the protection of chronology. The constancy of the speed of light leads to consequences that defy common sense and everyday intuition, especially with regard to time. The phenomenon of time dilation is one of the most tested predictions of Einstein's relativity. He states that moving clocks tick slower than stationary clocks. For everyday speeds, such as those of a car or airplane, this effect is infinitesimal, but at speeds close to $C, time can be slowed down to dramatic levels. This concept is personified in the twin paradox, where a brother travels into space in an ultra-fast spaceship and returns decades later, discovering that he has aged only a few years while his twin on Earth has become an old man. Although it seems paradoxical, time dilation is a physical reality proven by experiments with atomic clocks on airplanes and GPS satellites. Without relativistic adjustments for the difference in the passage of time due to speed and gravity, the GPS system would accumulate errors of kilometers in a few hours. Gravity also acts as a time dilation mechanism. The greater the mass of a body, the more it deforms spacetime and the slower time passes in its vicinity. Near the event horizon of a black hole, time dilation becomes infinite from the perspective of an external observer. A falling object seems to freeze forever at the edge of darkness. In the framework of modern physics, the passage of time is not absolute but is instead influenced by motion and gravity through different scientific contexts. Under the principles of special relativity, time dilation is primarily caused by relative velocity. This results in an effect known as kinetic retardation, mathematically expressed as $t equals t/gamma$, where time slows down for an object as its speed increases. When considering general relativity, the focus shifts to how mass curvature, or gravity, affects the temporal flow. In this context, the main cause of time dilation is the presence of a gravitational field, leading to gravitational retardation. This effect becomes most extreme in the presence of black holes, where the infinite density of the singularity causes an apparent time freeze for an outside observer looking in. Finally, the table highlights the unique status of photons. Because light particles travel at a velocity equal to $C, the speed of light, they experience what is described as subjective time zero. From the perspective of a photon, travel across any distance occurs instantaneously, as time effectively ceases to pass at that velocity. The question of time travel, especially to the past, is where light and causality face their greatest theoretical challenges. Stephen Hawking proposed the chronology protection conjecture, suggesting that the laws of physics will always find a way to prevent paradoxes, such as the case of a traveler preventing their own birth. Hawking argued that any attempt to create a closed time loop, a trajectory to the past, would cause an energy feedback loop, possibly photons accumulating infinitely, that would destroy the time loop before any object could traverse it. Paradoxically, we are all time travelers. Because light takes time to travel, we never see the universe as it is now, but as it was in the past. When we look at the moon, we see how it was 1.3 seconds ago. When we look at the sun, we see the past from 8 minutes ago. And when we observe the Andromeda galaxy, we see an image from 2.5 million years ago. This barrier of the now is absolute. Light grants us access to the past, but prohibits us from instantaneous knowledge of the distant present. In practical terms, space exploration is time exploration, and telescopes are our tools of cosmic archaeology. The concept of chronology protection also extends to the physics of information. Even in phenomena like quantum entanglement, where particles seem to communicate instantaneously across vast distances, the light barrier remains firm. No useful information that could violate causality or allow time travel can be transmitted faster than $C. Nature seems to have imposed the speed of light as a fundamental rule to ensure that the history of the universe is written in a single direction, preserving the logic and structure that allowed the evolution of intelligence capable of questioning those same laws. The evolution of perception and cosmic consciousness. Human biology is not a passive observer of the universe. It is the result of a 500 million year interaction with sunlight. The evolution of the human eye is one of the most elegant examples of how life adapts to the physical properties of the cosmos. It all began with patches of light-sensitive cells in primitive aquatic organisms, which allowed them to distinguish only between day and night or identify the shadow of a predator. Gradually, these patches deepened into cavities to detect the direction of light, evolving into chambers with lenses and corneas capable of projecting sharp images. Scientifically, The human eye is a photon detector of near-quantum precision. Under ideal conditions, the retina can detect the impact of a single photon, although the brain generally requires a continuous stream to register a conscious image. This sensitivity allowed our species to develop vision as the primary sense for understanding the world. Interestingly, the cells that today form our photoreceptors, cones and rods, have an evolutionary origin linked to cells that previously functioned within the brains of invertebrates, suggesting that the act of seeing and the act of thinking are deeply intertwined from the very beginnings of life. The evolution of biological vision has progressed through several distinct milestones, beginning over 600 million years ago with the emergence of photosensitive cells. During this earliest stage, vision functionality was limited to regulating circadian rhythms and phototaxis, allowing organisms to distinguish light from dark and move toward light sources. By approximately 550 million years ago, the development of the eye on the cup, an invaginated pit, enabled more complex behaviors, specifically direction and motion detection, which provided a significant survival advantage. Significant anatomical improvements followed as the structures became more sophisticated. Around 500 million years ago, the appearance of primitive lenses allowed for focus and image formation, moving beyond simple light detection to actual visual representation. This complexity increased further roughly 400 million years ago with the development of the vertebrate eye, which introduced the ability to perceive color and depth of vision. Finally, reaching the present day, modern human vision has evolved to encompass aesthetic and scientific perception, allowing us not just to navigate our environment, but to interpret it through complex cultural and analytical lenses. The connection between light and human existence goes beyond sensory biology. Carl Sagan and Brian Cox frequently emphasize that we are the cosmos knowing itself. The carbon, oxygen, and iron atoms that circulate in our blood and compose our DNA were produced in the agony of stars that exploded billions of years ago, scattering their enriched contents throughout the galaxy. These elements were subsequently captured by gravity to form the sun and the planets, and solar energy, light, was the engine that allowed the organization of these atoms into complex and conscious structures. This perspective transforms light from a simple physical phenomenon into a metaphysical link. When an astrophysicist observes the glow of a distant galaxy, he is using atoms forged in ancient stars to capture light emitted by other ancient stars and process this information in a brain that is itself a product of this cosmic process. Light defines our existence because it is the source of our energy through photosynthesis and the food chain, the basis of our perception through vision, and the limit of our exploration through speed $C$. Consciousness, in this context, can be seen as the moment when the light of the universe finally found a mirror. Through science, we cease to be merely butterflies floating in the wind and become navigators of the cosmic ocean. The understanding that we are made of stardust should not make us feel insignificant, but rather profoundly connected to every atom in the universe. As Neil deGrasse Tyson reflects, knowing that the universe is within us is a thought that makes us great, for our existence is proof that the cosmos can, through light, awaken and contemplate its own beauty. The end of the journey, entropy, heat death, and the last glimmer. The final trajectory of the universe is governed by the second law of thermodynamics, which dictates the inexorable increase of entropy, leading the cosmos from a state of intense brightness to a vast, cold, and desolate future. Carl Sagan reminds us that we are precious from a cosmic perspective, because in a universe of 100 billion galaxies, intelligent life capable of understanding light is a rarity that must be preserved at all costs. The heat death of the universe represents the climax of light's journey. A time will come when stars will exhaust their nuclear fuel, and the last sources of photons will be black holes slowly evaporating through Hawking radiation. Stephen Hawking offers an optimistic reflection when he says that we are just an advanced species of apes on a minor planet of an average star, but we are capable of understanding the universe, which makes us something very special. Brian Cox describes the end of time as a state where the arrow of time will cease to exist, because without change, without light and without heat, the past and the future will become indistinguishable in the permanent vacuum. The big question that remains for the observer and the scientist is how we will use the brief moment of light that has been granted to us. Will we continue to wander on the shores of the cosmic ocean, or will we become the species that has finally deciphered the absolute mystery of existence? The ultimate call to engagement lies in valuing knowledge. Science is the beacon that allows us to navigate the darkness, and each new discovery about the light is another step in understanding who we truly are in the vast theater of time.